Okay, so if there's no questions, let us start then. Right. So okay, so let me put things in in organized in perspective of what we're doing, what we're going to do now. So we define this function pi of x to be equal to the number of prime numbers of say p prime times p smaller or equal than x. Right, and the theorem we're going to prove is the prime number theorem. There is this theorem that says that pi x grows exactly like x over log x, right? Where exactly like means, if I divide one expression by the other, I'm left with something that goes to one. Okay, and so we defined a few other functions that I'll need. So we defined this function v of x to be p smaller or equal than x log p. And then we showed a few things, and I gave these things some numbers because we're using a reference so that you can go and look at the reference, right? So we showed a few things, so we get the right numbers. Okay, so we showed that v of x, or let me see this way, we showed right that v of x is bounded by a constant times x, right? Is O of x. There is a constant such that this is bounded by that constant times x. Okay? And so this was sort of dates back to Chebyshev. Is in a way, right? In a way, it is almost a prime number theorem. The prime number theorem would say that would be to say that Vx grows exactly like x. This says that it grows at most like a constant times x. Okay. And so we also showed, let me again get the right number. Okay, so this didn't have a number in that. So this was number 3. And we also showed that this doesn't have a number, so I won't give it a number here, that showing that v of x grows like x implies the prime number theorem. Okay, so this is what we did last time, right? So, in the way Chebyshev shows that, right, v of x is bounded by a constant times x, and also that it's bounded below by a small constant times x. And in fact, these constants weren't so big or small. They were like, 0.9 something and 1.1 something. But we're going to prove exactly that, that this is exactly the number of primes. So we're going to prove exactly the prime number theorem. And we're going to do this by proving this, right? So the goal for today, right? So I should maybe say goal for today. Right, goal for today is to show that this function grows exactly like x. Okay, so this is what we'll do today. Is the strategy clear? If anything is not clear, please go ahead and interrupt. So just 1 second. I have a slightly different setup. Okay, so now okay, so we need to define like complex analysis of how to arrive. I mean, I showed this very much at the end, the functions we're going to define. And one function we're going to define that's going to play a big role is the Riemann Zeta function, right? So this is going to be, so okay, so in this area of analytic number theory, people use S to mean the complex number. So S equals sigma plus IT for a number. So we'll use that rather than Z equals X plus IY. And so this function is defined in the following way, right? It's a series, and we know we saw by Weierstrass's theorem, this is easy to show that this is convergent, right? And, absolutely and uniformly converges on compact subsets, right? This is known as the Riemann Zeta function. Okay, so let me make sure this is not, doesn't look like a 5. Okay, so this is known as the Riemann Zeta function. Okay, and we're going to have another function that's sort of going to be useful, like an auxiliary function, which is this phi s is going to be equal to some p. And again, every time I say p, I always mean prime, right? Every time I always mean prime. P is always prime. It's going to be a prime number. And here we have log of p over p to the s. Okay. And clearly these functions, right, it's very easy to see that these functions are absolutely, right, they're absolutely and locally uniformly convergent, right? And they converge uniform in any compact subset. And right, so I can say something like locally uniform. Right, they converge on each compact subset. Convergent for S with the real part of S bigger than 1. Right? Right? This is easy to see, right? Because these sums converge, right? I mean, if we want to understand the absolute value of these summands, right, then it's enough to look at the real part of the exponent, right? And if S is bigger than 1, if we think about this over the reals, and if S is bigger than 1, then we know that these series converge, right? We know that the harmonic series, the 1 over n, doesn't converge, but 1 over n to the 1 plus 1 converges, of course, and so these all converge for S bigger than 1, right? And here, this series is clearly bounded by the series in which you sum over all the numbers, not just the primes, right? To see that this one converges is very easy because this is, of course, bounded by just a series where, I just take it over all the numbers rather than the primes, right? Because this series can only have more numbers. And so, of course, this also converges. Okay, and so in particular, from this Weierstrass theorem that we saw that these two functions, right? These two functions are analytic or in this half space. Real part of, oh, I have z, but I mean s, sorry. I'm gonna get confused a few times. Real part of s bigger than 1. Okay. Okay, and so, okay, phi s clearly seems to have something to do with prime numbers. The prime numbers show up, but actually, I mean, we're mostly going to deal with the Riemann Zeta function, and it's not obvious as of now what does it have to do with the prime numbers, right? Why did we define this function, and why does it have anything to do with the prime numbers? And so this comes now. Okay, so the first, there's going to be many ingredients to this, right? We're going to prove. Right? Our goal is to prove that this, right? Our goal is to prove this, that Vx grows as x. And the way we're going to do this is via complex analytic methods. And we're going to start by showing properties about the Riemann Zeta function. And in particular, we're going to be interested in doing in understanding analytic continuations of it past this half space of real part bigger than 1. Right? In particular, I want to understand better what this function does as for, say, real part positive. Okay? And then I'll mention a little bit about what the Riemann hypothesis is. Okay. And so first, let's relate the Riemann Zeta function let's relate it with the prime numbers. Okay, give me a second, because maybe there was something on the chat I didn't see. Okay, there were a few questions. Yeah, I can't, okay, for the YouTube link, I can't seem to get OBS to talk with YouTube for some reason. I'll try at the break. Okay, when did we show 3? Okay. we showed 3 on Friday. So the way we showed 3 was by, right, I can write the strategy here, right, was simply we showed that if you have a number n, that, right, so how did we prove this? Right, the only thing that needed to be done a little more careful is because, you know, I grabbed the number n and I did sort of some induction dividing by 2 over and over again, right? But the number might not be divisible by 2 many times, but it's easy to just go to, you know, you divide by 2 and you move either to the integer above or below and everything works just fine. Okay, but so the idea being that, right, the idea for the proof was that 2n choose n, right, is this needs to be divisible by every single prime number between n and 2n, right? Because, you know, what is this? This is 2n factorial divided by n factorial times n factorial. The top is certainly divisible by any prime smaller than 2n, and the bottom cannot be possibly divisible by any prime bigger than n. And so this is bigger than any prime, right, between 2n and n. Right? On the other hand, this is smaller or equal than 2 to the 2n. Right? And so from this, you just work out things, you take logs and you work out things a little, and you see that the number of primes here needs to be smaller than something that depends here. And so if you take the logs, you see this. Okay, so I won't redo that again, but this was the was elementary trick. Right? Elementary doesn't mean easy, it just means doesn't use anything fancy. It was just yeah, it was just a trick. Okay. Okay. I mean, if you take, right, maybe it's easier even to see here because we did it for pi of x, but for v of x is even easier. If you just take logs on both sides of this, right, say take log base 2 on both sides of this, what you get 2n on the right, on the left, and what you get here is exactly the sum of log base 2 of p, right, which is exactly v of x up to the constant that switches the log base 2 to the log base e, right? And so you get something like n is bigger or equal than v2n minus vn, and you just do recurrence that way. Okay, is the proof clear? Okay, great. Yeah, if anything is not clear, I mean, this part is just sort of extra material for fun. So, you know, interrupt all you want. If anything is not clear, we should, yeah. I don't want to get, you know, go down a rabbit's hole of too much detail in a proof because otherwise we won't finish. But so I don't want to do things that are clear, but I still can spend 30 minutes moving expressions around when everyone sees exactly what's going on. But if something is not obvious, then great. Okay, so how do we know that this converges? Okay, so the question is great. I'm glad there's some questions, right? How do we know that this converges? Right, so take you know, take this, right, log n, say n to the s, right? Or I mean, the way this should be proved really is right, to prove this properly, we would do this, right? So this now, you know, take absolute values. This is the same as, you know, taking log p and now taking, sorry, p to the s, right? But this is smaller or equal than doing this absolute value, or not absolute value, sorry, real part, sorry. Okay, real part of s we called sigma, so let's just switch this for sigma. Okay, and now, right, and now if this is, say, I mean, there's many ways of doing this, but you can, let's say sigma is, right, sigma is bigger than 1 for sure. Okay, so now take, you know, you can, certainly this is smaller or equal than some constant, right? I mean, there's a few different, you can, okay, so one way to do this is log n over sigma is certainly smaller or equal than log n, right? N sigma minus epsilon for any epsilon, right? For any epsilon and n big enough, large enough, right? Because n to the power epsilon is always going to beat the log, okay? And without the log, sorry, right? Right? And so you just pick epsilon, right? You just pick epsilon so that you have 1. Sigma is bigger than 1. Just pick epsilon so that you're still bigger than 1. Say pick epsilon here, right? And now you have a series such that this is bigger than 1, and we know that those series converge, right? This I'm sure you've seen in, in just normal analysis, but you can just compare it with an integral, right? The way this usually is proven is by comparing to an integral. Okay, yeah, thanks for the, it's not always easy to see what are the things that are clear and what are not. Please ask if something is not clear. There's really not much to, this proof has evolved for like, I don't know, 100 years, and so it's now quite slick and doesn't really use very many fancy tools, but the original proof is very complicated. Okay, all right, so, okay. Ugh, this eraser keeps erasing things that it shouldn't. Okay, all right, so we have these two analytic functions in bigger than, right? They're analytic in RS bigger than 1. So let's now relate the Riemann Zeta function with primes, right? And so this is done by what I'm calling 1. Okay, so this is the place where you use the product, the infinite products, right? It's the reason why I wanted you to see infinite products in the class, right? And is that this shows the relation between the Riemann Zeta function and number theory, right? And this, I believe, goes back to Euler, actually, this formula. Right? This is equal to p prime 1 over 1 minus p to the minus s for real part of s bigger than 1. Okay, and this really shows the connection between between the Riemann Zeta function and number theory. Okay, and this is key. This is really the thing that makes the whole argument work. Okay, so let's prove this. This is sort of quite easy to prove actually. So it's easier to see, maybe I should say, it's easier to see, right, that say 1 over zeta s is equal to, right, let's just remove the, take 1 over and everything. Okay, and it's also easy to see that this converges, right? Right, because we saw that the products, infinite products converge basically if and only if if we write it as a product of 1 plus some term, if and only if the sum of those terms converge, right? And so if s is bigger than 1, then the sum of 1 over p to the s, sorry, I keep putting the things on the wrong place, p to the s converges, right? And so then this product will converge, will absolutely converge even how we called it, right? And so it's easy to see that this converges for the real part of s being bigger than 1. Okay, exactly by this things we did with the log, right? Because of. Okay, so how do we? Maybe something pretty neat that is worth making a point is that it immediately follows here that there cannot possibly be infinitely many primes, right? This will immediately imply, right, that there exists infinitely many primes, right? There are, there are infinitely many. Of course, there are many much easier ways of proving this, right? There's argument that goes back to Euclid, but still, it's kind of neat that you can get this immediately. Right, so how do we get this? Well, just look at what happens in s equals 1. Right? For s equals 1, if you go look at the definition of the Riemann Zeta function, it cannot possibly converge, right? We know that the harmonic functions diverge, right? The harmonic series diverges. So if you go look here up, you see that this will diverge, right? 1 over n, the sum of 1 over n we know diverges, right? and so for s equals 1, zeta of s cannot possibly converge. But if there were infinitely many primes, there would be absolutely no problem in taking s equals 1, right? The formula would certainly be finite here, right? But that can't possibly be the case, right? And so this will immediately imply that there are infinitely many primes. Is a very unnecessarily complicated way of proving such a thing, but nonetheless, it does give that. Okay, so how do we prove something like this? Maybe I should say easier to see that it converges from this expression. Okay, so how do we prove this? This is easy to show, right? We're going to prove directly the formula above. Right, so zeta x, right, is equal to the sum for n from n n from 1 to infinity, 1 over n to the s, right? And we're thinking always of the real part of s as being bigger than 1. Okay. But now from every number is exactly one way of being written as a product of primes, right? This is the basic theorem. I think maybe it's called the fundamental theorem of arithmetic. Right? Certainly, a basic theorem in number theory, right? And so this means I can write this through their right. I can write this via exactly that by taking the primes, numbering the primes from 1 all the way to infinity, and now taking the sum over all possible choices of exponents for the primes, right? So and now I just have each n can be represented by the product of this type, right? Where only a finite number of them are finite, right? So let's say I don't know, I need a dummy variable, right? Okay. Right? And every number n is written in exactly one way in this form. But now, just by distributivity, I can rewrite this as, okay, this takes a second to see, it's easier to just look at it and see, right? I'm just going to use distributivity. And this is exactly the same as saying that there's a few different ways of proving this statement, by the way, but right, so I claim this. Okay, this is maybe the kind of thing, right? You're taking a product over a sum. This distributivity property will give you exactly what's above. Okay. It's the kind of thing that you just need to look at it for 30 seconds. It's easier than any word I might say. Right, and now what is this sum? Right, this is just, you can view it via the Taylor series, for example. Right, this is exactly 1 over 1 minus p minus s. Right, by say Taylor series, for example. Right, so this is used all the time in linear algebra, for example. Right, when you want to do understand the inverse of 1 plus a small matrix, you sometimes take this expansion. Okay. So this is the product p prime 1 over 1 minus p to the minus s. Okay, and this proves the part one that we wanted. Okay, this there's not much to it. This step takes you a second to see. Just yeah, take that second right now. Right, but you get a product, you get a sum over all possible choices of different r's for different p's, and it's exactly what you have here. Right? Okay. Okay, so now we have this statement. Okay. This holds only for the real part of s being bigger than 1. Okay, so let's now, for now, there's not really any complex analysis just yet. Right, there's some convergence of products, which I guess we saw in this class, but there's not really much complex analysis. Okay, so let's go to what's called, I mean, don't worry too much about these numbers. This is just in case you want to go back to the paper to know where we are. So what we're going to prove now is we're going to show that, we're going to talk about analytic continuations. And in particular, what we're going to show is that zeta s minus, so zeta s clearly, like the whole point is that, maybe let's stop to talk a little, right? So I have the complex plane, right? And I have here the s equals 1, the real part of s equals 1 line. And what I showed is everything is okay here. Right? And what I want to do now is analytically continuate this function over to this side. Right? I'm going to talk about an analytic continuation of it. Right? So we know that, if a function can be analytically continuated, there's only one possible way of doing it, right? Because it's not like the function could have certain values in this part of complex plane, and then there could be two functions that match here but don't match over there, right? Because the identity theorem tells us that if two functions match, in a place with an accumulation point, then they must match everywhere, right? And so there's only one way to analytically continuate a function, but it's not obvious that the function has an analytic continuation on how we get it, right? So usually at some point there was a very interesting question and discussion on the forum about when is it that one can analytic continuate functions and so on. I mean, it's a very hard question to, given a function, ask if one can analytic continuate it. I mean, the Riemann hypothesis can be formulated in that way, and many problems can be formulated in that way even. But if you have usually the way that one argues that the function is possible to analytic continuate is by just constructing a continuation. And this is done usually by two ways. Either by writing it as some kind of series and then trying to massage the series in a way that it's kind of clear that you can still define a series for that other place where you couldn't before. And then because that is an analytic function, it must be the analytic continuation. Or by some kind of formula. Right? Maybe you have some formula that relates, the zeta function with some other function, and then you define the function for the rest of the space via that formula. Right? This is another way of doing it. You have to argue that the solution to the formula is analytic. So as you may know, you can actually analytic continuate. I mean, except for some singularities. The Riemann zeta function all the way to the negative real part, right? You can analytic continuate all the way up here, right? There's some zeros in the real line and so on. Let's not talk about that for now. Okay. And the way you do this, so there'll be two things, right? We'll go and we'll work on understanding this function, right? Going from the real part 1 forward. And then there is a functional equation that gives some symmetry, right? And it tells you that around a certain line at the real part of half, there is a way to say what the function should be on the left side from what the function should be on the right side. We're not going to talk about any of that because that requires things that we didn't talk about. It's not really needed for the prime number theorem. And understanding, and even formulating Riemann hypothesis and so on, we can do everything just on this side of the line. But so for those of you that have seen stuff about the zeta function on the other side, with a functional equation, you can then say what's going on. Basically, there's a way of relating a zeta of s with zeta of 1 minus s. Okay, so that being said, we're going to try and now push the function over there. So how do we do such a thing? So we know that there is a pole, right? We know that there is a pole here, right? Because we know that 1 over n goes to infinity, right? And so there's definitely a singularity over there, right? And so somehow, if you want to analytic continuate, we need to do it meromorphically, or we just can take away that singularity, right? Like in calculus of residues. And so what I'm going to show here is that if I take away that pole, right, and with the residue 1, basically, then this extends analytically or holomorphically, or sometimes it's called holomorphically, same word. of s bigger than 0. Okay, so how do we do this? Right, we do it via a series. Okay, so let's prove this. So again, remember this function, this zeta of s is not even defined, right? We haven't even said anything about what it is for values of s whose real part is smaller than 1 or even equal to 1, right? We haven't said anything about what that even means. So how can I talk about something being extended, like being able to extend something, right? What I'm going to say is that I'm going to write zeta of s minus 1 over s minus 1 equals some function. Someone asked me if it should be, I don't think so. If there was a typo on the place where I'm extending it. No, it should, yeah, no, this is correct. Right? So there's a whole, yeah, okay, I got a question. I don't know if everyone saw it, but yeah, there's a whole thing, as I said, there's a whole thing to negative real part, which is actually not so hard to do, but for our sake is not really important. We can restrict to positive real part. This is where all the interesting stuff happens. So, okay, so how do you show that something like this, that one can extend such a function to an extra place, right? We're going to show that we can extend it, here, where I don't even have no idea how to even define it there, right? Right, the only sort of extensions that we did before was when we had a removable singularity, we took it away. I mean, this was an analytic continuation in a way, but it was clear what to do, right? Because you just take the limit, right? If you have a point where the function isn't defined, you just take the limit and you say, oh, the function is now valued this at this point, right? But here it's not obvious at all. Like, sure, maybe for the real line you take the limit, but how are you going to say what the function is valued here? Right? It's not like you can take an accumulation point of some. This can be an accumulation point of some sequence where you have the function defined, right? It's a real problem. And so what you do is you write it as some kind of series, right? It's maybe a different series or some kind of infinite product, something like this, and then argue that that series matches the function the way that you define the function on the place where nu is valued. You argue that said series it makes sense all the way up to the imaginary axis, and therefore it must be the analytic continuation. Right? This is the type of argument. Okay, so let's see it because this is simple, and you'll see the kind of argument. So it's a good thing to see. Okay. 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 So for the real part of s bigger than 1, right? We have. Okay. Sorry. Still, clearly, I'm not a number theorist. I always have trouble writing the zeta. Okay. Okay. So this is just, we're still in the place where we understand. We know what things are, what are the values of things. So that's okay. S minus, okay, 1 over s minus 1. I'm going to write it because, I'm going to, well, you'll see very soon what's going to happen. Okay, because this is equal to 2x, right? This is clearly, if you look at this, what is this? This is like if you take the primitive of this is just, right, 1 minus, over x to the s plus 1, or minus 1. Right? And so, right, and so this is equal to s minus 1. Okay, so I'm just writing this number in a different way, right, with the integral. Okay, so this is equal. Okay, but now what do I have? Now I think you're probably already seeing what's going to happen, right? Oh, I should put n from 1 to infinity. Right now I just split this integral on the right in its pieces, right? The point being that I have here a sum of 1 over n to the s, and I have here an integral of 1 over x to the s. Yes, from 1. Thank you. someone pointed out that this should be 1. Thank you. Now the point is that I created some kind of cancellation, right? Because this sum and this integral are things that are very similar, right? So let's exhibit this cancellation. Right? And the point is that the error of this cancellation will be of order something like 1 over ns plus 1, and that will converge for a real part bigger than 0. Right? That's the trick. Okay, from n to n plus 1, 1 over x to the s dx. Okay. Okay, so far so good. Right. Now let's show that that this converges absolutely. Let's move this. Maybe let's make this a little bit more. Let's put the integral. Let's move the 1 over n to the s inside the integral. Make things a little bit nicer. Okay. And now we just show, right? We show that this. Show that this converges absolutely for s bigger than 1, right? But that's easy. Okay, so let's do that. So now we have the integral, right? Just some simple analysis. Okay, so now, let's see if I remember the trick. Yes, so we take, so now the trick is to realize that this is itself an integral, right? And so let me write it, and you'll see it in a second. Right, because this, maybe I should do, right, this integral, I should use a different color to make sure, right? This integral here is just minus 1 over us from x to n, right? And so, because it's just a primitive of that, and so you get exactly what's on the left-hand side. But now I've already managed to put the s plus 1, right? So that now this starts converging for when the real part of s plus 1 is bigger than 1, and not when the real part of s is bigger than 1. So we're basically all done, right? So then this is smaller or equal than, so for each one of these terms, you get that the smaller or equal than the maximum, right? Over, I should say over all u, right? Between n and n plus 1. Right, of the absolute value of s over the absolute value of u s plus 1. Right, because this integral is an interval of size 1, the other one is of size smaller than 1, so certainly this is smaller than this, and so this is just like the right, I just need to take u, I want this to be as big as possible, so I want u to be as small as possible, so this is just s, and I replace u by n, so I get n of the real part of s plus 1. Right? And so the series is bounded by just taking the sum, right? This series here, let me see if I can put everything on the board at the same time, right? This series here, right? This is bounded by this here. bounded in absolute value by S in real part of S plus 1, right? And so absolutely convergent. Convergent for the real part of S bigger than 0. Right? Okay, so question about this. Right? Okay, so I'll get there in a second. Let's see if everything else is clear. Right, absolutely convergence, and of course, locally uniform too, right? Okay. So the question was here, right? So the integral, right? This integral, this is just smaller or equal than the length or the area of the integration of the area of integration, right? But in particular, this expression, okay, maybe I can make this a bit more clear, right? So let's justify this, right? So smaller or equal than just the area of integration times the maximum value that you get inside of the integral, right? But maybe I'll just do this way. N plus 1, right? N x. Okay. Now, I can certainly put the max here. Or maybe let me do one step at a time. I'm missing a dx here, of course. Right, this so far is clear, I think. Okay. And then, now, of course, I can just take the max. Right, so this is just smallest and the maximum possible value you can achieve. Right, but u is always between n and n plus 1. Right? And now this is smaller or equal, like this number now no longer depends on the integrand, right? Can move outside of the integral, right? And so I get, okay, let's move it here. Times just, the integral without anything in it. Right? But this integral is smaller or equal than 1, and this integral then is also smaller or equal than 1. Right, because I'm just integrating. Okay, great. Yeah, thanks for the questions. This helps a lot. Okay. All right, so I'll erase this, the triangle inequality stuff. Okay, give you, I guess I don't need to, yeah, I don't need to erase. I can just go to another page. Okay, so basically then, this means that once I look at this function, okay, let's go back conceptually, right? So once I look at this function here, zeta s minus 1 over s minus 1, then, for s bigger than 1, it is equal to this series here, right? And this series converges absolutely, right? And locally uniform everywhere on the real part of S being bigger than 0. Therefore, I can always extend, right? Therefore, I can always extend this function here, right, to analytically to the positive real part, right, by just defining it to be this new series. Right? And the definitions match for when the real part is bigger than 1, and so they need to be the same function, right? And so we prove that this analytically extends analytically to the real part of S bigger than 0. Okay, so it's 11, so I'll stop here. But what we're going to prove now is that, okay, so part of what we're going to prove now, just to give you a little teaser, is that we'll show, among other things, that that zeta of S is not 0 for let's say for all s, for s such that the real part of s is equal to 1. So we just show that we can analytically continuate the Riemann zeta function, right? So let's say that this is 1, right? We defined it on this side. Now we showed that I can extend it once I subtract 1 over s minus 1, I can extend it all the way there. So it means in particular there's a pole, a simple pole, and we know the residue, right? It's just 1, it's the residue of 1 over s minus 1, right? So we know that there's a pole there. And now what we're going to show after the break is that there are no zeros in this line, right? So no zeros in this line. And this will give us a prime number theorem. Now, the way we're going to show no zeros in this line will take us 20 minutes, maybe. I mean, in this paper, it's like 2 lines, but it takes a bit to process the 2 lines. But the original proof, I think, was something like 25 pages of analysis to argue that there's no zeros in this line. And the celebrated Riemann hypothesis, which is perhaps the most famous problem in mathematics, is saying that this is true all the way up to what's called the critical line, where the real part of s is equal to a half. So basically, the Riemann hypothesis says that there are no zeros, not just in the real line, where the line where the real part is 1, but actually all the way here. And that all the zeros, or all the non-trivial zeros, need to lie exactly in this line. That there's nothing in between the 2 lines also. And turns out that this gives a stronger version of the prime number theorem, which I'll describe probably only on Friday. Okay, so let's take a 10-15 minute break, and then we'll be back. I'll stick around a bit in case there's questions.